Okay, so let's take a look at a brief history of telephony. So to begin with, we're going to take a look at what was a traditional PBX or post branch exchange. And the PBX was something uh, that came along to try to privatize what had become basically too large to manage at a central office. So when the telephone company was connecting every individual person together, and they were doing all the work. At some point, the users or administrators in larger companies and corporations decided that they wanted to have more control over the features, wanted to be able to connect users with telephones directly to each other. Sorry, wanted to be able to connect users directly to each other, and like I said, have more control over those features. So they came up with something called the post branch exchange, and the idea was to emulate a central office. And if you take a look at the two different sides, really, if you will, of a PBX or a corporate phone system, it's really divided into two sides, and we have basically the station or line side. And these are the line cards that connect to the phones, both analog and digital, which the digital are typically proprietary to each individual vendor. And then we also have the trunk side. And the trunk side are cards in the PBX that connect to the local carrier, the PSTN as we call it, which is the Public Switch Telephone Network, or also might refer to it as the CO or central office, or possibly could connect to another PBX, another enterprise phone system, maybe in another building, on a same campus, or maybe even across multiple cities or across the world somewhere. And these are done through entities called tie trunks. So we've really got these two different sides. And then we also have a number of accessory cards. Now, with a post-branch exchange or a PBX, everything flows through what's called a TDM backplane. TDM is time division multiplexing. So we're basically taking all of these either analog or digitized conversations, and we are what's called multiplexing them or muxing them. And what that is that we're taking a lot of these different conversations and putting them back to back to back of each other, and using these different time slots. And so everything has to pass through the actual backplane, the actual physical backplane of the PBX. And so this gets into what's called a blocking architecture, where we actually cannot, in most large deployments of a traditional PBX, we can't actually have all of the phones that we have connected and all of the trunks that we have connected talking at once. There's really not enough, if you will, there's not enough bandwidth. So this is one of the disadvantages to the old PBX architecture. All voice traveled over dedicated separate wires to the PBX, separate from each other, separate from the data network. All voice inside that PBX, as I just mentioned, had to go through that backplane, and so it caused congestion at peak times because it couldn't support enough channels or time slots for every phone attached to make a voice call. We're going to take a look at analog voice circuits and what those are, and we're going to just take a brief look at them. We will get a lot more detailed in the CCNP voice class, but we'll go over everything that you need to know to begin with and for the CCNA voice exam. So first of all, we have what's called an FXS, or foreign exchange station. This uses a two-wire tip and ring, or single pair, and it uses it in a what would be called the standardized RJ11 type port. This typically connects to an analog phone or possibly a fax machine, and it also connects to an FXO port. So FXS and FXO are, for lack of a better term, basically the male and female of the voice world, of the analog voice world. So a foreign exchange station port is actually something that we would connect an analog phone to. So an analog phone acts like an FXO device, but connects to an FXS port. Okay, I hope that makes sense. An FXS port on a PBX, either traditional or even when we're going to talk about unified communication, it provides power in order to be able to power up that analog device, power the microphone and the speaker. It also provides negative 48 volts for ringing, and it provides things called call progress tones. So ring back, ringing, and dial tone. This basically acts like the central office to a given analog phone. Now, we're not really going to talk about digital phone ports for the old PBXs. We obviously will talk about their equivalent, which would be Cisco IP phone ports, but those are nothing more than Ethernet ports, as we'll come to see a little bit later. But if we did have digital phones on an older PBX, then this is where they would connect to, something like an FXS port, but instead of being analog, it would be digital. For our analog FXO ports, or foreign exchange office, it also uses a 2-wire tip and ring, RJ11, and this is what we connect to the central office. So the central office basically provides us with an FXS port. We can either connect our FXO port to their central office FXS port, or we could connect an analog phone. So what's the benefit of connecting an FXO port versus just connecting an analog phone? Well, if we connect just an analog phone to the to that trunk that they provide us, then all we're going to be able to do is answer that call at that one phone. If we connect an FXO port to that FXS port that they provide us, then we can switch that call back and forth across our PBX, traditional or unified, and send that to multiple different phone endpoint locations. So FXO provides something called supervised disconnect. We'll talk a lot more about this later, but the gist of that is that it basically watches the analog signal, and it tries to sense when the connection has been set up or disconnected rather. And if the other side did not disconnect properly, then it goes ahead and provides that supervised, it's watching the line, it provides that disconnect. It also supports caller ID. Okay, so the ability for the carrier to send in caller ID or calling number information, and we can take that and pass that on. There's also something called E&M. This stands for either ear and mouth or earth and magnet, depending on who you talk to. And this uses a 4-wire. So the middle pair are tip and ring, just like an analog. And then the outer pair are the actual E&M signaling. And this is typically used for a number of different things, like a tie line to another PBX. This is in both PBX and unified communications, where we would connect a paging source or music on hold live feed source. But most historically, this has been used as a tie line to another PBX. And the reason is it not only has that analog middle pair, but it also has out-of-band signaling that's used on the outer pair of wires. So it gives us a lot more control. Looking at digital voice circuits, digital circuits obviously carry information in what are called channels, and there's 2 main types of channels. There is what's known as the bearer channel and then the data channel. And the bearer channel is what actually carries the voice sample over. The data channel is an out-of-band, or possibly we have, we'll take a look at in the 2 different types here in just a moment. The data could be carried in band with the bearer channels. But this is the call control, the signaling. Should a call hang up? Should it start and open a new channel? And there's 2 main types of digital circuits. So we have what's called channel associated signaling, or CAS, as it's sometimes referred to, and then also common channel signaling, or CCS. An example of common channel signaling, as we'll talk about a little more, is something called a PRI. And CAS is very different than that. We'll actually go over that in the next slide, so I'll save talking about that anymore right now. So time division multiplexing is used on all circuits, and the idea is that in a digital world, and we're going to go over this actually a lot more, is voice conversations are sampled, and then they're cut up into slices and interwoven with one another. Okay, so the idea is we are listening, or the hardware, the DSPs or digital signal processor hardware is listening to your conversation, and it samples that conversation. And then we cut those up, like I said, into slices, and because we can carry so many in a certain amount of time, we interweave those together. And that's the idea of dividing and multiplexing multiple conversations together over a given amount of time. So looking at the digital voice circuits a little more in detail, we talked about CAS and channel-associated signaling. In this type of a digital circuit, voice and data are both carried on the bearer channels, so there really is no separate data channel. Each bearer channel is basically robbed of individual bits, or borrowed, if you want to call it, in order to transmit the data alongside the voice. CAS is sometimes also called RBS, or robbed bit signaling. So the idea is we borrow certain bits on any given circuit or on any given voice bearer channel, in order to instruct the other side what to do, whether there is calling or called party number, if we are asking to hang up the call or start a new call or put the call on hold. And an example of this is something called T1 wink start, or also in the E1 world, the European, really most of the rest of the world, is known as E1R2. That's the CAS format for E1. T1 has a number of different signaling mechanisms that can go over it for CAS. So looking at common channel signaling, on our voice bearer channels, the only thing that is carried is the actual voice samples. Data, or signaling about the voice, is carried on a single common channel. And an example of this is a T1 or E1 ISDN PRI, as well as an ISDN BRI. So a PRI being something that has, depending on whether it's T1 or E1, either 23 or 30 channels of bearer voice, and then the dedicated data channel, or on a BRI, also known as a basic rate interface, we have 2 voice bearer channels, and then we have a single data channel. So looking at something called a circuit switched network. So this involves 2 nodes, either 2 phones, or a phone and a central office, or possibly even 2 central offices. And they establish a dedicated channel or a dedicated circuit in order to talk back and forth. The circuit remains connected for the entire duration of the call. So as long as the call's up, there is a dedicated pathway. And it actually acts as if they were physically connected through an electrical circuit. Sometimes they are, just depending on how small that channel is. So with a public switch telephone network, or PSTN, this is basically the largest circuit switch network in the world. For those of you who are coming from the data side, this is kind of like the internet, but instead many telephone companies' switches are connected together with TDM circuits using the SS7, or System Signaling 7 protocol, or data. Now, obviously, most of the current world is moving away, even in the carrier, even in the PSTN, from this SS7 signaling. In fact, I think a representative was from AT&T appeared before the U.S. Congress about 2 years ago and said that within 10 years, they predicted, they were a pretty high-ranking person in AT&T, they predicted that all analog and digital communications would be dead and everything would be IP. Don't know exactly how accurate that is within 10 years, but the idea is that we're moving away from this circuit switch network and we're moving to something that we'll look at in a moment, which is a packet switch network. So some of the advantages and disadvantages to circuit switch networks. One of the advantages is there's a constant connection. So we guarantee that if a channel is available, every bit from each voice sample will arrive at the other side. So the bit rate and the delay, they both stay as a constant. And because of that, quality is inherently excellent. It's superb. The disadvantages are that there's not always enough voice channels available. So if you've ever heard about, hopefully you haven't experienced yourself, but maybe if you've heard about some sort of natural disaster happening in somewhere, some part of the world, and everyone tries to get on their mobile phones, their cellular phones, and try to make a call, it's possible that the carrier doesn't have enough channels, whether they're using the traditional circuit switched or even the new, enough channels open to complete the calls. So this can be certainly a limitation, and this is also what we were talking about with the traditional PBX. PBX uses a circuit switched architecture, and so with that TDM, or time division multiplexing backplane, we very well run into a blocking architecture where there is not enough physical circuitry to be able to handle, and clocking to be able to handle everyone talking to everyone else at the same time. Also, the bit rate is limited. So although the bit rate stays constant and it stays at a fairly high quality, there's no or little chance for newer technology to improve sound quality. So one of the things that we'll look at in the newer unified communications or voice over IP is that we can actually get better than, in terms of quality, and something we'll look at called opinion scores. We can actually get better quality than we've ever had, than we can even have with a dedicated older circuit switched network. And another disadvantage is that we have to bond multiple channels together if we want to enable video. So if you've ever worked with traditional video, video conferencing, H.320, we had to take multiple BRI or at least multiple B channel, whether they were part of a BRI or part of a PRI, and we had to bond those together in order to allow enough bandwidth or width in our time division multiplexing in order to allow a video signal to look decent. So looking at the packet switch network, the alternative, this is a digital network that transmits data, irrespective of the content, into various blocks of data that we obviously know called packets. So layer 3 devices carry these packets and encapsulate them into various types of layer 2 frames, whether it be frame relay or Ethernet or what have you, ATM, whatever. Of course, those are called cells, but anyhow. Each device then makes decisions on the network independent from the previous layer 3 or even previous layer 2 switching device, and it determines where the packet or frame should be sent. And then the internet is obviously the largest of these, but of course there's many private enterprise networks that exist. So some of the advantages and disadvantages to a packet switch network. The bit rate stays constant. That's one of the advantages, but it's also not limited. So newer technology can improve the sound quality, and indeed we'll look at that in what we call codecs a little bit later, and how different newer codecs can improve the sound quality from the usual status quo or what has always been. It's also a lot easier to increase bandwidth for a lot of different features, whether it be presence-rich status communications or presence, like I alluded to, or video, okay, high-definition video. And quality of service is really the thing that allows us to overcome all of the disadvantages that we're going to look at. So the disadvantages being no dedicated connection. So there's not really a hard electrical dedicated circuit between two ends. Instead, we're sending packets back and forth. And as we'll talk about, we're sending those over UDP. So they're typically sent connectionless. So that means that we don't guarantee that a packet gets to the other side, but that's where we bring in quality of service to mitigate that possible disadvantage. And again, there's no guarantee the packet will ever arrive. The possibility is there for packet loss. Now, in a properly designed network, you're not going to have packet loss, okay? Because you're, one, not going to transmit your voice over the internet. And if you do, then you accept the inherent risk of packet loss. And certainly not for an enterprise network. And two, we're going to design and engineer our circuits properly, and quality of service will make sure that we don't have any dropped packets. Now, there's not always enough bandwidth available. So just like with a circuit switch network, when we said in the case of some sort of a natural disaster or possibly even some sort of large event, Michael Jackson dying, for instance, was something that downed Twitter because there wasn't enough server bandwidth available. Well, if it would have been 10 years ago, maybe everyone would have been calling each other to talk about it, and there might not have been enough circuits in a traditional PSTN circuit switch network. We have that possibility in a packet switch network as well. However, it's much easier to add IP bandwidth than it is to add TDM backplane or circuit switched or PBX backplane. Now, another disadvantage is that delay can occur at various router hops along the way, and it can and often does greatly vary. The delay can vary from router to router or hop to hop. Delay is known as delay or known as latency. Delay variance is known as jitter. So the fact that we might have a delay of 10 milliseconds at one router and then 25 milliseconds at the next router, and then maybe we go over some sort of serial connection and we have 60 milliseconds at the third router, not cumulative, but just individual, from point A to router 1, 10 milliseconds from point A to router 2, 30 milliseconds from point A to router 3, 60 milliseconds, something like that. That variance in delay is known as jitter. So that's a term you'll want to be familiar with. And because of that jitter, if we just knew how much delay, then as long as it wasn't too much, we could buffer that information at the far end receiving device and then play it back smoothly. But with the variance, the difference in all the jitter, in all the delay, then we can't just buffer a set amount. We actually have to take into account all the different variable amounts of delay. Again, quality of service and proper design and engineering can overcome all of these disadvantages. So looking at a unified communication network, everything flows over the same network as standard data. But as we just mentioned, quality of service keeps the unified communication packets prioritized. So voice calls, we might have hardware-based, meaning I have an actual hardware IP phone, or I could have a Mac or PC type software-based client, so a soft client such as Cisco Unified Personal Communicator, CUPC, or Cisco IP Communicator, CIPC, or any of the various free or third-party paid-for SIP soft clients that are out there. And hardware-based, obviously, for voice calls would also deal with video calls and video conferences and video endpoints. So whether it be any of the various telepresence line or even, anything that has audio and or video over it, we're going to flow over the standard data network. Voicemail is going to go over the data network, presence and instant messaging. So we have a lot of ability with IM, with presence, with directory services, and even with phone-based applications. So whether those be web-based like XML or Java, midlets, whatever type of applications we can now put on our various unified communication endpoint devices, IP phones, wireless IP phones, video endpoints, and these can all flow over the same data network. So taking a look at public providers, unified communication systems can still connect to the traditional public switch telephone networks, but they can also connect to newer VoIP providers. Now, that's not to say that the older PBXs could not connect to the newer voice over IP providers, such as an ITSP or Internet Telephony Service Provider. They could, but with the old architecture, your voice or your IP enabling an old TDM architecture. With the way that Cisco approached this, back when they first got into the voice over IP game, back in 1998 when they acquired Celsius Systems, which was the company that had created the product of what was known as Call Manager, is now known as Unified Communication Manager, so Cisco's main call control server. When they first got into this, they said, listen, all of these traditional PBX vendors such as Nortel and Avaya and Siemens, they're seeing that voice over IP is going to be something big, and they're trying to, and this really wasn't so much in 98 as when Cisco got into it, but more in 2002, 2003, as those other manufacturers are trying to jump into the voice over IP business. The way they're approaching this, Cisco was seeing, is that they're trying to IP enable their existing TDM backplane, their time division multiplexing backplane. And the problem is that if you're going to run voice over IP, you really can't just piggyback that on. I mean, you can, but you still have all of the inherent disadvantages that we just talked about with a circuit switch network type environment. And so building the ground up as native IP data and your voice going over that natively, it was really a far better option. So again, you can connect some of the older PBXs depending on the version of code you're running and the various line cards that your PBXs support to newer voice over IP providers. But when you take a look at both side by side, doing a true unified communication solution and true voice over IP, building it from the ground up that way, has for going on a decade now made a world more sense. And of course, connecting to ITSPs use either the SIP protocol, which you'll become very familiar with, or the H323. It's a little bit older protocol. It's in some circles, you might hear people say that it's a lot more stable than SIP. That's because it's been around for a lot longer. However, we'll take a look at both of them in comparison to each other. I'll just go ahead and briefly say at this point, SIP is certainly mature enough that it is equally as stable and feature-rich as H323 at this point. So they're both good options, but most public ITSP providers that you would have a voice over IP connection with these days would use SIP. So looking at voice over IP just in general, the idea is we're taking analog voice, okay, so the actual waveforms that come out of our mouth or video, and we're sampling them, and then we're not really taking the entire audio stream that you would see, the entire analog waveform that would essentially come out of someone's mouth, the acoustic, but we're taking individual samples, and we're encoding those into a digital value, ones and zeros, of course, for transmission in a data payload of an IP packet. So voice over IP uses both a signaling protocol and a separate media protocol. Signaling being, what do we want to do? Do we want to start a call? Do we want to tear down a call? Do we want to hold, resume, information about the call? And then media being what actually carries the audio and or video signal. And we use these both to comprise the overall VoIP conversation. Now they're transmitted separately. So I just mentioned what the signaling protocol does. And when the signaling, the setup, or the teardown is successfully negotiated, specifically when the setup is successfully negotiated, then that's going to be what results in the media transmission. So a media protocol is going to sample that voice or video using something called a codec. We're going to talk a little more about this in the next slide. And it's completely independent from the signaling, and it's sent using UDP. So again, it's connectionless. The signaling is typically, not always, but typically sent using TCP, or a connection-oriented three-way handshake I know that I'm talking to the other side, and if for some reason I don't get a packet from the other side that I know I should get, then I'm going to tell that other side to retransmit the lost sequence, the lost packet. UDP being connectionless, I basically send the IP packet out into the world, and I hope that it gets to the other side, but I have no acknowledgement, no mechanism like I do in TCP to let me know that I'm receiving, that the other side received that information, that packet properly. Now, there's a really good reason for us using TCP for the signaling and UDP for the actual media or the voice or the video. And if you think about it, it's incredibly important that the other side get every single bit of information about the signaling. So if they accidentally missed one packet, and maybe I already have a call set up, for instance. I've already established a TCP three-way connection, and I've already got a voice call set up, and I want to go to hold that call. And so the side A transmits to the side B to hold the call, whatever various signaling protocol you might care to think about, or just the theory in general, since we actually haven't talked about any of those codecs yet, any of those signaling protocols yet. But I go to transmit a hold. I tell the other side to hold. Now, that hold the information, the signal for the hold may come in a single packet, or it might come spread over a series of packets. Either way, let's say one packet drops. For whatever reason, there's packet loss on the network. If it had all the information about the hold, well, then the call doesn't get held. But the original transmitting side would think that it did get held. Or maybe it just doesn't have part of the information, and so, one packet gets dropped, and so the receiving side all of a sudden only gets part of the message hold, and it really just doesn't make any sense. Either way, it results in the call not being held, but the transmitter thinks that the call was properly held. So the problem with this is the call's not held, but the transmitter thinks that it is, and that can obviously lead to all sorts of problems. Maybe I say something that I didn't want the other side to hear, or maybe I'm trying to transfer the call to somewhere else, and it hasn't actually been properly held yet. So the need for a connection-oriented and acknowledgement-based protocol, such as TCP, should probably be quite apparent in a signaling setup, teardown type of a protocol. Now think of an actual media protocol. Any protocol that's going to be, what we use is something called RTP, or the real-time protocol for all media. But if my voice, a part of my voice, doesn't get to the other side, you might argue and want to believe that it's absolutely critical that every single bit of information from my voice gets to the other side. But the rate at which we're sampling these packets is so quickly, we're sampling like 8,000 times per second, and we're putting bits of that information into multiple packets. And so if you dropped one packet, it might sound something like this, where there might be a little blip, and you probably didn't even hear anything. You could even drop multiple packets, and maybe something like that, where you hear, something that's messed up in the voice, and it might disrupt your conversation. Obviously, this is where proper QoS engineering comes in, but it might disrupt your conversation, but the majority of your conversation is going to go on. Now, you might argue that that's quite critical. And I would say then engineer your quality of service and networks properly. Don't send voice over the internet. But the point is that let's step back and take a look. If I drop that small part of voice or video communications, would it make sense to have the receiving router or receiving endpoint stop all communication, say, whoa, stop everything you're doing, buffer everything, which could be quite large, and retransmit that one tiny little packet or 2 or 3 packets that were dropped. And then it has to, once it gets those retransmitted, after it gets the sending side stopped, gets those other packets retransmitted. Then it has to reassemble them in the proper sequence and then go ahead and empty the buffer and start allowing that hearer, the receiver, to hear everything again. It really doesn't make any sense. It really would cause communications to pretty much grind to a halt. So while we want to engineer our networks properly, we want QoS to work properly, and we're certainly going to talk about that a little bit in CCNA, a lot more in CCNP voice. While that's critical and very important, the very nature of the underlying UDP protocol, it's very important that we use that, because going through that scenario again of stopping the sender from sending everything and retransmitting just for 1 or 2 or 3 packets is actually a lot more detrimental to the quality of the call than if those 1 or 2 packets were simply dropped. So that was just a quick talk about why UDP for our actual media. So taking a look at the idea of a codec. Codec is or stands for compressor and decompressor. So the idea is that the codec is what takes and carries the voice or the video. The compressor is used in the transmit direction. That is, we sample the video and then we compress it. And then when that video or voice is received, we decompress it. So the decompressor is used on the receive direction. The codec is carried inside of the media stream. And I already alluded to this. We use the protocol called RTP, which stands for real-time protocol. Now, just a couple codecs they could include, but they're certainly not limited to in any way. These are just some of the more common ones that we tend to use. The G.711, G.722, G.729, the ILBC, and the ISAC. We're going to talk a little bit more about these. So the G711 codec, this was something that was developed by the ITU. Now, in unified communications, most things were derived from one or the other side of the camp. Either the ITU, which is the International Telephony Union, also known as the ITUT sometimes. This is the group of engineers that basically started or modernized the public switch telephone network as we know it. So these are the guys that created the ISDN protocol, that perfected, the engineers that perfected a lot of the electrical signaling between FXO and FXS analog ports and connections, as we talked about. And so they're more the traditional telephony guys. Now, they've certainly come into the new voice over IP world with things like codecs, things like various voice over IP signaling. H323 is an ITU signaling protocol. It's based on ISDN. We'll talk more about that later. But that's one side of the camp, the ITU. The other side of the camp is the IETF, the Internet Engineering Task Force. And these are the guys that brought you TCP/IP, right? This is the Cisco's and various companies around the world and individual contributing engineers from these companies that came together and produced the RFCs, the requests for comments, what we're familiar with from our routing and switching CCNA, or if you've done CCIE route switch, then you're obviously very familiar with that. So those are the two sides of the camp. So IETF comes up with various signaling protocols such as SIP. Okay, so we're going to talk about, and they come up with various codecs as well. Some codecs are come up by completely third parties, not necessarily independent, independent, but not necessarily associated with one of the two. But those are the two main camps, aside from the independents, that we'll talk about, is the ITU and the IETF. So G711 being an ITU standard, it uses something called postcode modulation, or PCM. This is a 64 kilobit per second default bit rate. It is really based quite largely around the ISDN single voice bearer channel. So if the if a single channel of an ISDN circuit was with speech capability, then it would be 64 kilobits per second as the default transmission rate, and it used something called PCM, or postcode modulation. G711 is based largely around that. It has excellent audio quality, and it's typically used on local area networks. This is not exclusive. It doesn't only have to be able to, but for the sake of the exam and for the sake of most situations that you'll look at, it is used on LANs. The G.722 codec is newer. It's fairly old by now, but it's newer. It's also an ITU standard. It is also a 64 kilobit per second default audio rate. However, this has actually been optimized for wideband speech. And we're going to go a lot more in detail on these in the actual CCNP voice lectures. But just going over hopefully what you need to know and an introduction to these for the CCNA voice. Now, so we'll talk more about what wideband speech is later. But G.722 using the exact same bit rate, and so therefore the exact same amount of kilobits per second for the actual voice over IP conversation, or the IP data payload, we actually get a far superior quality for G711. The reason is we're actually sampling, I'll just go into it briefly, we're actually sampling a wider spectrum of the audio frequency that's coming out of your mouth. Okay, this again is for LAN environments. Looking at G.729. Now this has a few different variants, but this has been largely what has been used for wide area network or WAN connections for many, many years. Now there's a lot of newer codecs and more people are beginning to switch to those, but you will still see G729 probably for years to come as just about the default go-to codec for carrying voice over a WAN. And you'll either see G711 or G722, probably G711 more, just because more devices support it on the LAN side. So G.729 is an 8 kilobit per second default rate. And this comes with something that's called high complexity for the CPU or DSP. So we all know what a CPU is, hopefully. If not, probably need to go back and take a CompTIA course or something. But a DSP, I alluded to it earlier, is a digital signal processor. This is a dedicated IC circuit that is, I believe they were originally developed by Texas Instruments. And the whole idea of the application-specific IC, basically, is to sample audio and put it into some sort of digitized codec format. Okay, so some sort of compressed, digitized format for transmission on either an IP network or, you even have DSPs in your home audio receiver, not necessarily for over IP, but it's still sampling that audio in order to use it in a digital format later. So when we talk about complexity, we're basically talking about how much strain it puts on a various DSP or the actual CPU. So if we're talking about a high complexity, then, and we even have very high complexity, we also have medium and low complexity, then we're basically saying it's going to require more chips or more DSP channels in order to take and compress or decompress voice or video into a various type. In this case, we're just talking about voice. These are voice codecs into a various voice or video type of a codec. So G729 by itself is high complexity. The ITU also came along and said, let's create something called G729 Annex A. So we're going to add a variant, and the whole idea behind this variant is that it has a medium complexity footprint. So the algorithm that's used to create the compressed digitized format is not low, but lower than the default G729 algorithm. There's also something called the G729B variant, or Annex B. And this, again, was a high complexity codec, but it added the addition of something called voice activity detection. Now, for years, we used to say VAD is bad, okay? VAD, or voice activity detection, was bad for a lot of years because it was used for really, really low bandwidth situations, such as maybe a 64K or 128K frame relay circuit between WAN branch sites. And the idea was that it tried to sense when you started talking and it sent packets, and when you stopped talking, it would stop sending packets. Now, the only problem with that, if you've ever played with a older, I don't even know if this term applies anymore. Gosh, this talks about how old I am. But the older walkie-talkies that were voice enabled or voice detected. The problem is it would cut the first part of a syllable off your beginning word or sentence as you began the voice. It's detecting your voice and it begins sending, but it begins just a tad bit late and it clips the beginning of your voice. And also it could clip the end of your voice in trying to too aggressively close that gate and stop transmitting the IP packets or the voice. So we used to say VAD is bad. Now it's come a long way, VAD in general. And if any of you work with telepresence or plan to work with telepresence, you will see that VAD is back. Okay, not bad anymore, but back. But in the voice world, especially for G729, we used to say VAD is bad. So, also the G729B variant added something called comfort noise generation. So when voice activity detection was enabled, in other words, I stop speaking, and so therefore it's not transmitting packets. If the conversation just goes completely quiet, like that right there, you might wonder, did I lose the connection? I don't hear anything. Did he stop talking, or what happened? And people are actually used to hearing in their ear, especially if you're thinking of the old, I guess some people still use it. I haven't used one in years, but the old handset on a regular or IP phone, doesn't matter, but the old handset, you hold it up to your mouth and your ear, and if all of a sudden you don't hear anything, psychologically people are used to hearing something. And so if all of a sudden they don't hear anything, they think the connection's been broke. So the G729B variant added comfort noise. So it was just a little hiss there in the background, kind of like white noise to let you know that something was still going on. Okay. So most people don't use or try to disable negotiation of G729B, but it is there, and some people still require it, actually. So some ITSP carriers require you to use G729B specifically for the bandwidth savings of VAD. So moving on and looking at the ILBC. So this is a much newer internet low bitrate codec. That's what ILBC stands for. 13.3 kilobits per second was the default rate. It's optimized for narrowband speech, so it's not going to have a terribly high quality. It's actually got a pretty good quality, but it's not going to have a terribly high quality, not like wideband speech like G722. And it was originally designed by Skype. Now, Skype's used a lot of different codecs. I'm trying to think what their most recent one is called. I just looked it up yesterday, but I can't recall right off the top of my head. But they actually designed this protocol originally, or this codec, and it was intended for the internet, or where we had packet loss or medium to high packet loss. And when I say high packet loss, we're talking, anything over 1% packet loss, but the internet as a WAN connection. And so it's optimized for that. It's got great what are called dejitter buffers that can handle putting those buffering and putting the speech back together at the receiving side. There's also something known as the ISAC, or Internet Speech Audio Codec. This is a even newer codec, and it ranges. It's a variable codec, variable rate, somewhere between 10 to 32 kilobits per second. It's adaptive, so it's going to adapt to the changing, basically the changing quality of the IP circuit. And it's optimized for wideband speech, but it's also optimized for jitter. As we said already, the difference in delay from hop to hop over WAN connections. So again, it was created for the internet, but created for wideband speech. So excellent quality, still a relatively low overhead. Even if you get up to 32 kilobits per second, that's still half of the G711 or G722 default rate, which is 64 kilobits per second. And obviously, it can go down to as little as 10 or 12 or 16 kilobits per second. So we've already mentioned what these are, but digital signal processors, DSPs, they convert analog to digital, or then again, digital to analog. So they do both the compression of the codec and the decompression of the codec at the receiving side. And we've already stated that they sample, they listen to the analog voice or video. And then they do something called quantization, which is basically approximating a continuous range of sampled values. So when we're continually sampling a waveform, an audio or video waveform, we've got a very large number. And we use a process of quantization to reduce that number to a much smaller number so that we can then encode a lot less data, but something that still represents the proper, appropriate original signal form. So then, like I said, we go to the encoding step and we convert the quantization or quantized values into digital ones and zeros in the codec. We compress them, and then we packetize them in the IP data payload. And we also have the ability to use compression, not just in the codec sense of compression, compressing the quantized voice, but we can actually compress the voice packet using various hashing algorithms. So a lot of these, or these functions, are what are provided in the dedicated analog, I'm sorry, not analog, but application-specific ICs or ASICs or DSPs. So now we're going to look at a term called Packet Data Voice Module, or PVDM. This is basically Cisco's version of a DSP. So these are Cisco proprietary DSPs. A lot of times in various talks that either I'll have or you might see written out there, you'll see people refer to DSPs, especially if they're talking about industry standard or cross-vendor type situations. If we're talking about PVDMs, it's really the same thing as a DSP, but this is just Cisco's version. Okay, so these are used in a number of places. There are PVDMs or DSPs in actual IP phones, so that when an IP data payload gets to a Cisco IP phone, the phone itself can perform the reverse. So if we just talked about what we do in order to get the call compressed and sent out on the line, we sample it, and then we quantize it, and then we encode it, and then we send it out on the line with optional compression. When we get to the receiving side, we do the opposite. We decode it, and then we play back that waveform, for the listener. It's also used in VoIP gateways for voice termination. So if I've got a voice gateway, a gateway that goes in between the IP, voice over IP world, and the older public switch telephone network, or PSTN. So this is where I might have some of these various analog or digital circuits that we've been talking about. In a voice gateway, which we'll find out is a Cisco router, then I might have an FXS port in order to go to an analog phone, or an FXO port to go to an analog central office circuit, or possibly a PRI, T1 or E1, to go to a digital PSTN or central office circuit that's got many voice channels. We also can use PVDMs in something called DSP farms. DSP farms are really, that's what they are. They are farms of DSPs. They're a large conglomeration of DSPs grouped together for the purpose of doing a number of different things, such as conferencing. Maybe I need to have an audio or even a video conference, and so I need to multiplex and mix, well, really not even multiplex, but mix together various audio streams from various audio codecs, maybe all from the same, maybe from different ones, as well as video streams and video codecs into a single audio or video conference. I also have something called a media termination point and something called a transcoder. And we'll talk a lot more about these later. Transcoder is a MTP. This is used from taking one codec and transforming it into another. We also have the ability to transrate and transsize. So I can take a G711 codec on one side, the sending side, and on the receiving side, maybe they have the ILBC codec. Okay, I can go in between those two with a PVDM. That is, I can code between them. I can transcode. I can also use various rates. So maybe one protocol has one rate, one default bit rate, and another has a different rate. Or in video, I've got multiple sizes for the video. Maybe I need to take a large video size, such as VGA, and reduce that down to QVGA. Okay, I can also transsize. All of this is done with PVDMs. Now, a media termination point, this is something that terminates the media for various reasons that we'll talk a lot more about, probably in CCNP voice. Probably don't need to know too much about these other than that they exist. But basically, if I need to put a call on hold, I might need to terminate that media somewhere so that then I can decide if I need to set up a new call, a new media stream somewhere else, and then transfer that call from the media termination point. It's sort of like, I thought I had a good example, but it probably wasn't. But anyway, it's kind of like, it's someone like walking into an office and telling them to sit down in a given chair until I bring someone else out to take them in. So that chair might be a temporary holding place, a media termination point. So taking a look at something we've talked about a little bit already, the real-time protocol, or RTP. RTP is the layer 4 protocol that rides on top of UDP, and it encapsulates all delay-sensitive traffic such as voice and video. So we use various UDP ports. There are 16,383 ports. They start at 16,384. And if you add 16,383 to 16,384, you get 32,767. So those 16,000 odd ports are what we use in the UDP range for our voice and video, for our RTP. There's also something called, and any of you that are security conscious might realize quickly, well, that's a lot of ports to open up in any sort of firewall or access control list. You're exactly right, and it's one of the reasons that in CCNP voice, we're going to talk more about security and how to mitigate or how to stop from opening 16,383 ports times however many phones that you might have on either side of a conversation, and instead only open that many ports. You still have to open the 16,383 ports, but only open them for maybe one or two IP addresses or nodes on either side. So taking a look at something called the real-time control protocol, or RTCP. So every time we have RTP, the real-time protocol, we also have, going right alongside it, the real-time control protocol. This monitors things like quality and statistics for the RTP protocol. And like I said, it's paired with the RTP stream. So it uses whatever the randomly chosen port for RTP was, whatever UDP port was used, we'll always add +1 for the RTCP. So maybe the RTP chooses UDP 20,743. Then the RTCP, the control, real-time control protocol, would be sent alongside of that at 20,744. RTP is always going to use an odd port, and RTCP is always going to be on an even port. So security by means of encrypting the voice data payload can be done using the AES cipher. This isn't going to encrypt the entire packet, such as IPsec would, but this is an option being performed by something called SRTP, or Secure RTP, and it uses TLS. TLS is basically SSL, but version 3.1. Okay, so if you're somewhat familiar with SSL, whether in HTTPS communications, web server communications, TLS, Transport Layer Security, is basically just the enhanced version of SSL. And so let's just take a look real quick here at how the encapsulation would look. So from the right, we've got our voice payload, and that voice payload is going to go into the RTP or have an RTP header attached. Then we're going to attach a UDP header, and then we're going to attach our layer 3 header, which is our IP header, and then we're going to put that into our layer 2.